So for the last while, we've kind of explored a lot with Newton's second law. We've looked at horizontal motion, we've looked at vertical motion, we have looked at two-body systems, the Atwood's pulley, the Fletcher's trolley. What we want to do now is we want to kind of do, I'd say, the dynamics equivalent of projectile motion, but not quite so intense mathematically. So what we're going to look at is we're going to look at the case when your object's on a surface that's neither horizontal nor vertical. Rather, we're going to have this case where your surface is at an angle. So this will present a little bit of challenge in terms of resolving forces, but what we're going to do is we're going to do a little bit of math magic to help us out with the situation. We're going to do what's called a rearrangement or a realignment of the coordinate system, and I'll explain that in a second. So what we're going to be looking at is we're going to be looking at this thing called inclined planes. So inclined planes look something like this. We have a surface that is inclined with some angle with the horizontal, and we'll have some object that's on this plane, and we will ask you questions about it. It may have friction, it may not have friction, there may be an applied force. There's a lot of variety and richness in these questions. Now, the issue that we generally have here is, well, if we use x and y, kind of like, x horizontal, y vertical, this is going to lead to a lot of trig, and it's going to lead to a lot of frustration. We don't want that. We want this to be as seamless as possible. What we are going to do to simplify our calculations is we are going to align the coordinate system to the plane. What that means is we're going to change what we call our x-axis, what we call our y-axis. So for us, the x-axis is going to be parallel with the plane, or parallel with the surface of the plane. And then the y-axis, this is going to be perpendicular to the plane, or perpendicular to the surface of the plane. So what we're trying to say for this, what we are used to using is something that looks like this. We might say this is x and this is y. And for most problems we do, that's okay. For the inclined plane, we're not going to use that. For the inclined plane, this is what we're looking at right now. What we want to do is we want to change the perspective just a bit. We want to treat it almost something like this. So in this case, we're going to have our x direction that's parallel with the plane, and we're going to have our y direction that's perpendicular to the plane. This is what we're going to have for a coordinate system. We're going to have x be parallel with the plane's surface, and we're going to have y be perpendicular to the plane's surface. What that's going to do is that is going to allow us to simplify the math. There's still some trig, but that's okay. We can handle a little bit of trig. So the first thing is we want to draw a free body diagram. And we're going to assume no friction for the moment. Friction is something we can certainly add in a little bit later. Now for this object here, we are going to have a force of gravity acting on the object. That hasn't changed. Even though the surface is inclined, the force of gravity still points directly down. That hasn't changed. What is going to change just a little bit is the normal force, because remember that the normal force is perpendicular to the plane. So what we're going to have is it's going to be 90 degrees to this surface. So we're going to say that the normal force looks a little bit like this. And we're assuming no friction, so this is good enough. Now, with this, what we are going to be interested in doing is we're actually going to be interested in resolving the components of the force of gravity. So we're going to break this up into two components. We're going to break this up into a component that's parallel with the plane, which is going to look a little bit something like this. Let me sketch out the components. So we're going to sketch out this component that's parallel with the plane. And we're also going to sketch out this component that's perpendicular to the plane. Now, to calculate these, we're going to have to make use of that angle somehow. So I'm going to show you how we do that. What we're going to do is we're going to draw the vectors directly on the diagram, and we're going to draw FG, Fn, all that again. So we're going to just draw it directly on here. So here's my Fn vector. And then I'm going to draw my FG vector. It's going straight down. And then I'm going to draw out those components. So I have this FG parallel that's acting parallel with the plane. And I have this FG perpendicular that is perpendicular to the surface of the plane. Now, I'm not going to show the proof for this. If you want to like try it out, you can certainly do a little bit of geometry. It's just the whole, if as long as you understand that all the angles of the triangle add up to 180 degrees, you're going to be fine. What you're going to find though is that this angle here, that is actually going to be the same angle here where we have this, sorry, it's going to be that angle between the force of gravity and the perpendicular component of the force of gravity. So these two angles are exactly the same. You will not be expected to prove that they are. If you want proof of it, you can certainly search that online. But yeah, it's a little bit of a geometry thing. So this diagram, if we were to kind of blow this up just a little bit more, here's the force of gravity. And then I can get components out of that. So this is just kind of like what we did in dynamic, or with kinematics, doing all the component work. So there's FG perpendicular. There's FG parallel. Now you might notice on the diagram I've drawn the FG parallel coming out from the dot here, from the center of our free body diagram. It's the same thing as having it placed here in this little diagram here. All we've done is shift this down, but these two are going to be the same thing. We're just placing it here to help us with the math. So there is our angle. Now what we want to do is we want to get some components. So for parallel to the plane, what you're generally going to know is you're going to know FG, because we know that that's mg. So the relationship between this angle, the parallel component, and the force of gravity, it's going to be sine of the angle. So we know that sine of our angle is going to be this ratio of FG parallel to just FG. Or I could say that FG parallel is FG times sine of theta. And then if you're so inclined, we could just say FG parallel is mg sine theta. Now, what this is giving us is the component of the force of gravity that's acting parallel to the plane. This is going to be responsible for bringing this object back down to the ground. It's not going to be the full effect of the force of gravity, so it's going to be a slight bit of it. So we're taking mg, multiplying it by sine of the angle. For the perpendicular component, the relationship between the perpendicular component, FG, and this angle is going to be cos of theta. So cos of theta is going to be FG perpendicular divided by FG, or we could say that FG perpendicular is FG times cos of theta. And then again, if you're so inclined, we can write FG perpendicular is mg cos theta. So this is assuming that the angle is defined from the horizontal. That's pretty much always the case with inclined planes. I've never seen a case where the angle is defined from the vertical. It doesn't really make sense contextually. But these give you the two components of the force of gravity. And if you want to check this out and see how this works, well, we could always check, if you're, sometimes the big mistake that students make is they mix up the sine and cosine here. Just take a look and see what you should get, or compare it to something that you would know. For example, and I'm just going to mark this on the side. So for example, if theta was to 0, we'd have a flat surface. So we'd have something that looks a little bit like this. So in this case, our force of gravity that's perpendicular to the surface would be as such. And then technically, my force of gravity parallel to the surface would be running along this line here. But we know that gravity only acts strictly down, so I'd actually have no component of the parallel force of gravity on a flat surface. Let's check our equations. Are our results going to make sense if we put theta is 0? Well, mg times sine of 0 is going to give us back 0. That's good. If I get FG perpendicular, that's equal to mg times cos of 0. Cos of 0 is going to be 1. What this gives me is FG perpendicular. This is going to be equal to mg. This is just the regular force of gravity, and that's what we would expect on a flat surface. The perpendicular component is just the force of gravity that we expect. That is one way to check to see if your answers, if you have the right trig function. For these on exams, you do not have to prove how you got these. Most students memorize them. The only thing you have to be careful with, though, is with memorization. Sometimes your memory, it's a little fickle. Sometimes you make mistakes. So be cautious with that.